I just wanted to thank Kevin, first of all, for inviting me to come speak. I think it's an excellent opportunity. Thank you, everyone, for attending tonight. I know everyone's got their own busy schedules, so thanks for taking the time to come and listen to me go on about my company to you. And I have quite a bit to go into. I know I'm not going to get to everything, but hopefully along the way, each and every one of you will get a little piece of something that hopefully you'll find interesting, glean some new insights, or maybe we can spark a conversation and we could pick up later. So that said, let's get started. I wanted to introduce myself first. My name is Dan Pompa. I am the partner manager for Quantinuum. My background, a little history on me. My educational background is in physics. I went to the University of Mississippi. I also minored in math, engineering, and computer science, and I was an honor scholar there during my undergraduate studies. And that's actually where I got started doing research in quantum machine learning. I was working in under a condensed matter theorist in his group, Dr. Kevin Beach at the University of Mississippi, and we were essentially what I did was I wrote an algorithm that would act like a quantum neural network. We wanted to build up something that architecturally was like a neural network, but had quantum mechanical properties that we could take advantage of. I have a link to the thesis on my LinkedIn. All this information is there too, so I'm not going to belabor any of this, just a brief summary of what I'm doing. Right now, I'm still doing research through U of M and at Southern Methodist University in quantum machine learning and in integrated photonics as well. I like to split my time between software and hardware. But I'm particularly interested at this moment in developing these cognitive learning and reasoning models of mammalian brains that incorporate some use of or interplay of like quantum information and computational methods. Professionally, I worked as an engineer and a data scientist at Raytheon. I was supporting the fabrication and this manufacturing processes for these AESA radar systems. So like those big radar systems that go in nose cones of fighter jets or on the sides of like naval ships that basically just send out these huge EM waves that
and if you could highlight this a lot, because I'm sure there's lots of us that want to hear more about it too, Dan.
Yeah, please. Maybe another time we can go into that. It's a fascinating technology. Like from an engineering standpoint, it's brilliant.
What was that, John?
Jamming.
Oh, radar jamming.
Yeah, so we did, radars and jammers. So it's a little bit separate in the intent of the use of those devices, but similar kinds of technologies. Essentially, they're all phased array radar systems. And yeah, just brilliant technology. But what I was doing is I actually procured about $250,000 in innovation funding to lead a team of engineers to build machine learning models to expedite and improve their near field tests of those phased array radar systems. It was a wonderful project. Lots of great things came out of it. I ended up actually getting picked up by an applied AI team out of Andover, Massachusetts, and we were doing a lot of similar kinds of things, doing image recognition. I did a lot of electrical parametric models, but supporting the same types of products. Ultimately, these mimic chips that would get integrated into circuit cards that go into those radars. Yeah, wonderful stuff. Personally, I am married to this beautiful woman that you see here in the corner. Her name is Cecily. I have 2 daughters. I have an 8-year-old girl named Penelope and an 18-month-old girl named Juniper B. And we are also expecting one on the way. And they tell me, fingers crossed, that it's a boy.
So, yeah, congratulations.
Thank you. Might finally get a boy. So I wanted to give everyone a brief overview of what we're going to talk about today. I wanted to go over the company, what we're doing, our intent within the quantum industry, so you can get a sense of how we see ourselves positioned within this emerging industry, the business model that we are structuring ourselves under. We are, if you got to see David Shaw's presentation, Fact-Based Insights from a couple weeks back, we are the closest to a full stack provider. So a software as a service provider, where we can do everything from starting at the hardware to building middleware to software solutions. And then end users never have to touch any of it if they don't want to. But that being said, we want, and our big motivation is to become what we call a center of gravity within the quantum industry. So we want our company to act as a sort of accelerant for everyone working in this industry and for all the industries that touch it as an extension. So if there's any kinds of opportunities for technological collaborations, research development, partnerships, you name it, I mean, please reach out to us, reach out to me anytime. And we would love to have conversations to see what we can do to support these efforts to help grow this industry. I'm going to take a lot of time to go over our products, our projects, and our collaborations. I wanted to give everyone an opportunity to see some of the things we're doing. We're doing a lot, so I cannot go into all of it in great detail, but if you follow up with me afterwards, I'd be more than happy to go into it in laborious detail, however much you're willing to listen to. But yeah, so I'm gonna go into that, and then finally I want to close out with what we're trying to do for growing our partnership program. Okay, so that being said, let's jump into it. What is Quantinuum? Quantinuum, as of right now, is the world's largest integrated quantum computing company, really the world's largest quantum computing company. We have over 400 employees at our company alone, which may not sound like a lot compared to enterprise businesses, but if you're aware of the quantum industry, that's huge. And over 300 of our 400 plus employees are scientists. And a large number of them, I think well over half of them, are PhDs. So we have a huge number of experts in really all the different fields that you can think of, from anything in hardware to any kind of applications in quantum software. We have some of the best minds working on that. And what that comes from is it comes from, at the tail end of last year, we went through a merger. And that merger consisted of Cambridge Quantum, which was a leader in building all of these different quantum software solutions, and Honeywell Quantum Solutions, which was Honeywell's quantum division. And it was actually kind of a natural progression based on the very collaborative relationship that Cambridge Quantum had with Honeywell. Cambridge Quantum was actually the primary users of Honeywell's hardware. And so it kind of just made sense that we would start to build into something, something more collaborative, more integrated. So they went through the process to spin off, Honeywell spun off the entire quantum solutions division and combined it with Cambridge Quantum to form its own legal entity, which is now Quantinuum. Okay. Any questions on that so far? Nope. Okay. And we are a global company. We are an ever growing. We span the globe. We have an office in Japan. We have offices in London and Cambridge. We just opened an office in Munich, Germany. We have a few offices in the US, in Washington, DC. And then we have our headquarters in Broomfield, Colorado, where a lot of the former Honeywell people are working on the ion trap hardware that we build. And yeah, and we're still growing. We're looking at building an office in France as well, and just, trying to touch every part of the globe. Okay, so let's level set everything and see where we're at. All of you are probably aware of the different hardware solutions. There's a lot of different approaches that you probably come across of all these different, from big companies to small startups, that are trying to tackle this quantum hardware development problem from all these different angles. And there's a lot of common types that I'm sure you've heard of, and I didn't include like D-Waves and Neil are here, but if you think about more like gate-based, something closer to like a processor on the compute side, you have your superconducting architectures, which are your big companies like IBM or Getty and Google. There are the ion trap devices like ourselves, Quantinuum, IonQ, Quanta, AQT. There's the folks doing stuff in photonics, the big leaders like Xanadu and PsiQuantum. And then there's a plethora of all these other different approaches that people are taking, just taking advantage of the quantum nature that shows itself in all these different forms that we see in materials. And that includes, cold atoms, neutral atoms, spin qubits, you name it. There's a ton of these different approaches. But as of right now, we make the claim that the ion trap hardware is leading in terms of efficiency and performance within this NISQ era. And I'm going to explain to you why we make this claim. And the big thing is when you start to think about how we measure the performance of a near-term quantum device, it's really not enough to just talk about the number of qubits that you have. It actually is kind of misleading. A lot of companies say, well, we build this hardware, it has so many qubits, but since the qubits work off this quantum nature that we see in reality, there's a lot of issues and errors that we have to mitigate just to be able to get any kind of efficient performance out of the devices. And so what we look at is a measure that IBM came up with is quantum volume. And quantum volume was an early stage of a way to try to encapsulate all these different performance metrics, some way that we could actually measure the devices in various ways to see how they were performing and actually come up with benchmarks to measure against so we can increase that performance over time. And that encompasses a lot of different things, the connectivity, how much error you have, fidelity. It's actually pretty complex the way it's devised, but it seems to be at this moment a fairly decent representation, a way to measure these devices. And this is a measure that at Honeywell, now Quantinuum, we've adopted as well. And as some of you may have seen recently, I think I mentioned it on previous talks, Quantinuum just announced that we achieved a quantum volume of 4096, which is very exciting, particularly because it is keeping us in line with what we projected we would be able to achieve over time. So what we were doing is in line with what IBM was trying to do, is kind of taking this Moore's law-like approach. It says like, oh, about every 18 months, you double the capacity of compute for these transistor-based devices. IBM says, well, we are going to take a similar measure and say we double our quantum volume about every 12 months. And then Honeywell, just based on what we were seeing in the rapid growth of the hardware development that we were achieving, claim that we can increase that quantum volume by a factor of 10 every 12 months. And that's what this graph here is intended to represent, those different trajectories. And you can kind of extrapolate from here where you'd see that growing into. Okay, so that's all fantastic. We're very proud, very excited about these developments with our hardware, but we're also very realistic with the stage that we're at right now. And the stage that the quantum industry is at in terms of hardware maturity is still well within the NISQ era. So that's these noisy intermediate scale quantum devices. They're essentially working within these constraints of there's really not that many qubits that you can work with. There still can be a lot of error. It's hard to maintain coherence of your quantum states, so you can't really run circuits or really deep circuits or have long run times for your circuits. So there's a lot, and then we have all of our issues with trying to build up error correction protocols and compiling code, and there's just a lot of limitations. But what Quantinuum is setting out to do, as some other companies are, is trying to see what we can do now with the devices that we have, these NISQ devices, and joining them with classical hardware to try to get solutions that matter today or within the next few years, doing proofs of concepts with companies to show that we can get some benefits, that we can start to see some advantage, and that as the hardware matures, we can easily scale up the solutions that we're working on now for the clients, customers, or partners that we work alongside. So our main avenue, and this is something that was developed at Cambridge Quantum, but I love it because it expresses the sentiment behind how we view ourselves as a company. So even though we joined with Honeywell Quantum Solutions, we're Quantinuum, we have this ion trap hardware that's, you know, claimed to be the most performant, we really want to maintain as much as possible hardware agnosticism. We want to support all the different approaches to developing hardware in any way that we can, because we're not laying our stake in any one of them particularly. I said earlier, we want to be that center of gravity for the whole industry. So we developed this compiler. It's called Ticket. And what Ticket allows you to do is to take whatever your programming language of choice, your quantum programming language of choice, or Python, if you're strictly classical in programming, you can take your code to where you write your quantum circuit. You can add one line of code that pulls in Ticket, and Ticket will optimize your code and your circuit for any of the major hardware simulator providers. And there's a lot of complicated math and graphical mapping that's happening in order for it to do that, but it has access to all of those hardware backends. So if you wanted to write your code and you wanted to run your circuit on any of the major devices, you can write into add Ticket, and then you can write in to add access to the backends of any of these major hardware devices or their simulators, and you can run it and you can cross compare and see what is the most performant. And it caters to each of them because their architectures aren't the same. The qubit alignment's not the same. There's a lot of differences, but Ticket accounts for all that and handles it all for you. It abstracts away that complicated process of optimizing your quantum circuits. And just as a quick comparison to some of the other popular alternatives to something like Ticket, here's just a quick graphic to let you see, you know, say you wanted to compare it to something like Qiskit. Well, Qiskit is set up to do some kind of similar types of optimization, but it's, you know, mostly set up to work with the IBM device or, you know, with our ion trap hardware. We have a very close relationship with IBM, so we work collaboratively together, but Ticket is much more across the board. And it really is just not accessing devices like D-Wave because D-Wave's an annealer, and there's no way that you can write gate-based circuits for an annealer. But for the most part, it can access all these different backends. And as new providers come out, we can take about a day, our team can go in and write the same kind of code to access those backends. And the really nice thing about this is all free. It's 100% open access. Anyone from an enthusiast to a C-suite employee at a major enterprise company can go in and start writing code now and use Ticket and get the most out of it, and by an order of magnitude above its competitors. So please definitely go just Google Ticket, TKET. You can pip install it whenever you want and get started with it. It's very exciting. We use this. We use Ticket as a platform. It's a basis for all of our products. All of our software solutions are scaffolded off of Ticket. So this allows us to do the same thing, work with all those different hardware devices, but from there we touch into all these different application areas within industry to really to cater to the different customers and partners that we're working alongside. And there's a list of these different companies that we've worked with for a number of different application areas. And these are the main application areas that we're working on now. We have a product in cybersecurity. We have a product we're building in chemistry. We do some of the world's only work in quantum compositional intelligence, which is fascinating. And I want to talk about that a little bit later. We have a number of algorithms that we write in quantum machine learning. And then we also do a lot of work in simulation and optimization. I have some stuff to go into that.
I have a question on Ticket, Dan.
Sure.
How does that compare? Is it, or does it compete with something like Classic's compiler or with like Fire Opal from Q Control?
So Classic's, this Classic is actually at a different stage in that process.
They're a different layer in the stack, I guess, right?
Yes, they're a different layer in the stack, and I think that they're using it. Like they are going to use Ticket,
Oh,
and it's being so it's not going to it's not really in competition with any other compilers that I'm aware of. And it's not intended to be. Like we don't monetize it, we make it open source. We really just want it to be very inclusive and to take advantage of what we've developed.
And then Dan, we had a couple questions. Ron had asked, is Ticket its own language?
Ticket is not its own language. Ticket is a C++/Python compiler. So it's basically like a mapping system.
So on a previous slide, I saw that it appears that it understands various input languages. Was it my imagination, or was Qiskit not a language available as input?
Qiskit is in that it works off of what's called QASM. And so the intent is that that's the ingestion, right? It can take in QASM, spit back QASM. And so if you think of Qiskit, what that translates to is like if you're writing code in the IBM Q interface, it's that same kind of syntax that you'd be using writing there. And you should be able to access, run Ticket. I don't know if it's through that interface, but through using the same kind of syntax and language.
Yeah, so again, on that previous slide, on the left side, you had like circ and some other, there you go, Q sharp.
Yep.
Oh, no, I guess you just had the symbol for it. Sorry. Yeah, you not the name. You have the Qiskit logo on the left. Okay, never mind.
Yeah. And I can go into that more later, or I can put you in touch. We have evangelists that, go around basically spreading the word of Ticket and explaining it to people. I wanted to take more time to explain some of the products that we're working on, because this is really exciting for us. We've actually identified ways where we can provide advantages using these devices now. And one of those avenues that we've identified is through our cybersecurity product called Origin. And so when you think about security platforms, at the base of any security platform are cryptographic keys, right? So if someone's able to break through all these different layers of a security platform, at the last stronghold for that security are the actual cryptographic keys. These are the things that, like for RSA, Shor's algorithm will theoretically be able to work out the factorization and break, right? What we're doing is we're using our devices now to essentially extract the entropy from the quantum states of the systems that we're running and inject that entropy into these random cryptographic keys that we build. And then we can disseminate that to any client or partner. But this is something that we've achieved that's unique for the first time ever, is these are verifiably non-deterministic keys. So this is something that's been difficult for the longest time within cybersecurity, is that we can say, oh, we generate these random keys, but what was the computer that it came from? Where, how do we know if it's truly random? We actually have tests. We run Bell State tests on our cryptographic keys to show that not only are they fully non-deterministic and essentially just unbreakable, is that they're future-proofed. And if you use them now, there's no way that any hacker or intruder is going to come back and be able to, in any algorithmic approach, any mathematical, any devised way you can think of, be able to come and uncover the whatever created that key, because it is truly non-deterministic. And we are developing ways to incorporate that in just a number of different application areas. And we have customers and partners across the board that are already incorporating these cryptographic keys. And just to give you a sense of some of that, we have worked with Fujitsu to secure some of their networks for government customers. So as you can imagine, that's a really big deal, and there needs to be a lot of reassurance there. So the fact that these companies are trusting the keys that we're developing is very significant. We're using it to secure blockchains, which is very exciting for me, just from that techie standpoint. And we also used it to help with communication, sending signals to the ISS, which is pretty cool. But we're partnered, we're working with some of the biggest players in the cybersecurity space, trying to develop solutions that will integrate and incorporate these cryptographic keys for mass use. And we have plenty to go around, and we can offer them through the cloud or a number of services. We can integrate to some kind of local configuration as well, depending on what the need is. There's a lot of opportunities there. It's very exciting. If you want to know more about it, please reach out to me and I can explain more. We are also, sorry, does someone have a question?
Oh, cool.
Nice. So we're also really putting a lot of effort to developing our quantum chemistry area. And in quantum chemistry, we have something called Human. So I mentioned this before, and a lot of you are probably aware that one of the most promising areas for applications of quantum devices is going to be looking at systems that are quantum in nature. And there's this famous quote from Richard Feynman where he said that, you know, nature isn't classical. If you want to make a simulation of nature, you better make it quantum mechanical. And that's what we're doing. We're taking the quantum devices that we're building up, software inspired and software quantum inspired quantum based algorithms to essentially do that direct representation of these small chemical quantum models. And what that's allowing us to do is not having to do what happens on the classical side of things, is having to do a lot of approximations. We can actually get exact solutions. We can simulate larger systems because quantum devices can encompass a lot more of the dynamics that are happening in, say, like a slightly larger molecular structure, and it scales well. So that's what Human is. Human is the state-of-the-art Python-based quantum computational chemistry platform, but it's essentially intended for anyone that wants to work and say, I think I have a graph here. So right now, to give you a sense of where things are at, if you do this classically and you wanted to get a good sense of molecular structure and all the dynamics that are happening from a chemistry standpoint, you really can't do that in a short amount of time, certainly not, and in any exact form or fashion for anything beyond these small scale molecules. What Human is allowing us to do is to scale that. We're actually able to scale to larger molecular structures, and we're doing this now. We have partners, customers that we're working on problems. We're actually looking at these bigger molecules and getting really interesting results out of that. So essentially what it is it's this platform that will allow you to go in and, basically design whatever the molecular structure you want to look at is. And we're working on all the ways that we can integrate that with various pieces of hardware using things like Ticket to allow customers or partners to, work with, whatever you're comfortable with to the extent that you want to take it. And here's an example of some of the companies we worked with. Total Energies, I don't know if anyone saw, we had a recent announcement. We were doing a big project with them for carbon capture. So they're trying to develop these materials that will help offset some of their CO2 emissions. And there's not really many ways that this can be, I'm going to say that it can't be tackled classically. It's just a very difficult problem to tackle classically that we're finding what we're doing with our devices and using a platform like Human, we're actually making some good headway in helping them find these new materials. So it's very exciting. And I love that it's also good for the environment as well. I think that's well in line with our desire as a company to affect positive change in the world. All right, so where am I on time? About halfway through. Okay.
You're pretty good.
Yeah.
So we did have a couple questions. So I think Helen and
Sure.
Root, there's a question about Pennylane, and I think Helen did too. So go ahead.
Oh, okay.
Yeah, Dan, thanks. Thanks, Kevin. But yeah, so I wanted to know where exactly Pennylane will come in the entire stack. So is that kind of an option or alternative to Ticket, or is that kind of falls in where Qiskit and other languages falls in?
So my understanding of Pennylane is a lot of its functionality was intended to work with building up quantum, like machine learning algorithms, doing some type of optimization. It's not doing compilation in the same sense. And a lot of what Xanadu does, I know with Strawberry Fields, I'm not sure to what extent Pennylane can be used, and maybe you can tell me. A lot of what they do is catered towards photonic devices. I think Pennylane is more agnostic, but I don't think it's a compiler in the same sense. I have never seen any comparisons with Pennylane and Ticket as doing any kind of circuit compilation.
I see. Yeah, because we've actually used Pennylane. Well, okay. So we were using Qiskit for IBM, but then to kind of, because IBM is not as versatile as Pennylane, we use Pennylane to test it on various different hardwares, including Quantinuum's hardware as well. Yeah. So
I was aware that I mean, that makes sense from what I've used Pennylane some in the past. It's been a while. It makes sense that you would be able to do that. I don't think it's going to achieve the same kind of functionality. And the reason being is Ticket uses a mathematical formalism in order to do the optimization of these circuits that is something that is very unique to us. And it actually falls in line with what I'm about to talk about, the quantum compositional intelligence. Our group, our chief scientist, Bob Koch, and our head of software development, Ross Duncan, actually formulated something called ZX calculus, which is a new mathematical formalism that works really well in quantum mechanics, also oddly works really well in linguistics, but is kind of the basis for how we're able to take something like your code, the quantum circuit that you've written, create a graphical representation, and then optimize the functionality of that circuit. So I don't know how Pennylane's functionality compares to that. I know I'm sure it's not doing the same thing, but I would love to see any kind of comparisons to see how it performs. Yeah, I'll probably look into that after this. If you come across anything, please share it with me. I think that's
okay,
really
of course.
Yeah.
Thank you.
So Umit had a question here. Go
Yeah,
ahead.
hi. Can I jump in?
Sure.
Oh, great. Hi. My question was about the cryptography keys your system generates. Like, what is the rate of the keys that you are able to generate? In seconds.
We have already generated all the keys that you could possibly need. We have if you're ever interested and you wanted to go into a lot more detail about that, I mean, some of that's proprietary information, but I could, share at some point, given like we signed an NDA and did all that wonderful stuff, I can share with you. But essentially, we don't need to use the quantum devices anymore at this point. We have a specialized injection process from what we took from the quantum devices that we can use strictly classically to inject, and then we can provide as many keys as you want.
And these keys are in form of like a strings of ones and zeros, right? Essentially a digital key that represents the very quantum random number generator, essentially the outcome of that.
Yeah, it is a quantum random number generator, but it's truly quantum. Like it's actually
to verify that information. You're able to verify the entropy level.
Yeah, we do Bell tests, and we can show, and we actually have done these demonstrations. So we can show how it works and actually verify, yes, that it is, that we achieve that level of entropy.
Okay, and how can this be used in QKD scenarios where you want to distribute the keys? I mean, because QKD also uses quantum random number generator,
Yep.
but it goes further than that by securing the actual channel. That's different than just generating a random number concept.
Yeah, I may not be the best person to answer that last question, but I can put you in contact with someone who can. I want to say yes, but I don't want to make claims of things that's not my area of expertise.
Thank you.
Sure. Yeah,
So-
please reach out anytime.
And we answered the question. So Ticket is based on C++, right? Not Python?
And Python.
It's both. It's
Oh,
mostly C++.
okay.
C++ is, like a low level language. So
Okay, is there anybody else that we haven't heard from? We saw Lorraine come in, Monica, Marlu. Any questions for Dan right now? This is excellent, by the way, Dan. It's almost like too much information, but
sorry. I know we do so much. I knew this like preparing, and I was like, gosh, we do too much, but I don't want to do a disservice by not mentioning something, because some people will be
No,
interested in
and
cyber.
it's really good because I think I'm joined with many people to say that we didn't know this stuff existed. So it's just really good to hear it. I do have a question. So how many units are available for users to use right now?
So, okay, so we're an IBM hub, so we can offer access to the IBM devices, and there's so many slots for those. For the ion trap hardware, you have to have a project with us.
A project. Okay.
Yeah.
Yeah,
There's no way to access that because it's so in demand and it's expensive. Yeah, that's a longer conversation.
okay. Well, that helps a lot of us kind of like, because we know about AWS bracket, at least, a
Yeah,
portion of us.
and so there are alternative avenues where you can get like credits and run off of our hardware. That's an option for sure. You can do that.
Are you talking like, I saw INQ has 20,000 credits, something like that? Or is that the one you're talking about?
Yeah, IonQ is doing the same thing. So through Azure Quantum, you can buy so many credits. I think AWS is another access point. You can buy so many credits and you can run off of our hardware and our simulators.
Gotcha. Okay. Very cool. You have more?
I do. If you can buckle up, and this is really exciting to me. I had to share this. This is not a product. This is something that is so wonderfully unique to this company, but is so exciting as a prospect that's going to come out of quantum devices and development. It's truly, it's very interesting. So another area of interest, and this is mostly academic research at this point under our chief scientist, Bob Koch, that I mentioned earlier, is quantum compositional intelligence. And so some of you may be familiar with natural language processing. Natural language processing is like the engineering application of computational linguistics, right? So trying to take this computational approach to understanding language and making some kind of use of that. Quantum natural language processing is the quantum analog to that takes advantage of some of the formalism from the mathematical side of quantum, but is a subset of what our team's working on, which is quantum compositional intelligence. And quantum compositional intelligence is this whole emerging field that's it's made accessible by this development of the ZX calculus that I mentioned, which is this totally new formalism of mathematics that allows essentially a deeper dive of areas in linguistics or in quantum mechanics, these systems, to get to underlying principles that are not easy to understand at a surface level. It's very hard to explain this, by the way, because it's complicated, but it's brilliant. But to give an example, this is an actual application that we came up with that you can go and engage with now. This is really fun. I don't know what use you can make of it yet, but it's still pretty cool. We developed something called Lambec. Lambek is this Python library that's like that QNLP toolkit that'll allow you to go in and basically just take any text and map it to a quantum circuit for whatever purpose you wanted to take that to. And like I said, this is pretty academic at this point, very exploratory, but the implications are profound. I'm not going to fill all the gaps for everyone because I already am taking up too much time. But if you get a chance, read into ZX calculus and some of this Lambek stuff. It's really cool.
So John had posted a link, everybody. So it's a Wikipedia page, just for your reference.
Yep. And so finally, this is not products, but algorithms that we develop. We do a lot of work. We have a dedicated team in quantum artificial intelligence and quantum machine learning. And we tap into all the different areas that you may have heard of where quantum machine learning is being used in industry. So there's a lot of promise and benefits of these algorithmic speed ups of quantum analogs of classical algorithms that we project to see well into the future as the devices scale. Once we get those fault tolerant, million qubit devices, we'll be able to, well before that with some of these algorithms, different scales, be able to get these quadratic and even in some cases exponential speed ups for things like search algorithms, which are ubiquitous. Things like that factorization is the same kind of sentiment behind that, requiring the scale. But what we do right now to find near-term advantage is we build these hybrid models. So essentially building a machine learning model, say you want to do some kind of like inference, you want to take some data and learn something from it so you can make a prediction about something that's going to happen in the future based on new incoming data. What we do with these hybrid models is you can build up your model, but you can offload the parameterization tweaks that you do to train your model onto a quantum device. So it's doing all that heavy lifting and then spitting back to you the parameters that you need and to build up that trained model a lot faster. And that's wonderful because there's, for big deep learning neural networks and things of that nature with, handling these big data problems, the compute time, the resource, everything that goes into it's very expensive. So being able to offload that onto a quantum device is a monumental achievement. And that's something that we're starting to do and find some benefit in doing.
Can I ask you a quick question on that?
Go ahead.
So if you go back to the previous slide, on the quantum part to the left, those are conceptually still parts and parcels of the classical deep learning models. The loss and gradient and the entire looping of classic optimizer, all of that. So in a previous discussion, you told me that you would help me transition from classical machine learning to quantum machine learning. So this is actually good for me to see that where things are to be as classified within the classical framework, and then where you might want to go, how you're defining the quantum jump from classical machine learning. So I guess my point is where you're showing under the quantum umbrella of some of the things, at least conceptually, are, I think, parts and parcels of classical deep learning already, aren't they?
Yes, they're very analogous. You can think of the quantum devices a lot like an external processor. Like when you do a lot of say tensor calculations, it's a lot like that. It's just quantum and probabilistic in nature. And so you look to see advantages based on that probabilistic aspect of the device.
Yeah, I haven't forgotten your promise, by the way, just so you remember, Dan.
Anytime, honestly, anytime anyone wants to reach out to me, this is my favorite topic. So
yeah, it's like Sound of Music. These are a few of my favorite things. So I think Umit had a question, and then Root can go.
Yeah, I have one quick question about performance of this machine learning model. There's a company here out of MIT that does this called Zapata Computing. They have something similar to this. what kind of a performance optimization can you gain out of this tensor matrix multiplication when you move it into the quantum realm? Is it like a 10x, 100x improvement on the neural layers, or is it the actual propagation improvement on that side?
Right. So it depends on the problem and depends on what you're comparing to. And what we often do is because we're working with the NIST devices and they're limited in what they can do right now, we tend to have to shift the problem in such a way that we can make the comparison with the classical analog. So, I mean, it wouldn't make a whole lot of sense to say, oh, we're going to compare this high performance compute-based deep learning neural network to something we're doing on this little NIST device.
Okay.
There's going to be no comparison.
Okay, so there's no one comparison as of today, is what you're saying.
No, but there are other advantages, and it's not based necessarily on being able to iteratively go through a process like that, right? It's more based on the probabilistic nature of the devices that you're working with. And I can give some examples of that. One of them is in like GANs. So generative adversarial networks, there's a quantum analog to that called a QGAN, which is a quantum generative adversarial network. But the reason that it works so well is because all the qubits, the state of the qubits as it's defined, you can entangle all of them to achieve this higher state space, but each of those qubits has some probabilistic amplitude, right? And so you have this combination of all these probability amplitudes that you can use interference techniques to optimize for whatever it is that you're trying to get out of it, which is something that it's not really achievable to do that classically, right? Because you're going to have to do things deterministically classically. I think I have an example of, I have some supporting slides. If we get time at the end, I can show you the comparisons of some of the models that we've run, and you can see how the performance compares.
Dan, sorry, I just had a quick question. So it's kind of relating to the last point that you mentioned. So do you think that we require new ML-based models to fit into the quantum computing technology as well as the framework of quantum computing technology, or can we adapt already existing models?
You can do both. I think ideally there's going to be models that can be built up that incorporate a lot of the fundamental principles we look at and we get out of the quantum devices, but a lot of them are just models we adapt. There's something that we just, like I said, with those parameterized circuits, you're just offloading doing the parameterization.
Right.
You're still using classical models. You're just using any of the big popular ones, but you're, just offloading it to, do some processing. So yeah, there's, for quantum machine learning and optimization, a lot of that, I see it as always probably being somewhat hybrid. Just because the classical devices will always do really well to do certain types of computation. And it doesn't make sense necessarily to offload that onto a quantum device. It's just not necessary.
I see. Okay. Yeah, because I mean that makes sense. But also the thing is kind of if let's say a new model was developed that uses the quantum principles that is embedded into the model itself, then wouldn't that, I would think at least, that would perform significantly better than this type of hybridization where you're using some portion in quantum and while majority of the work is still happening in classical computing, because it doesn't make sense to, convert everything to quantum.
There would certainly be some advantages to that. But it also depends on what the advantage is. Some of the issues with something like, say, deep learning neural networks is that we can get, do these really complex calculations and inference and do all these wonderful things, but it's still like a black box method. It's not very comprehensive. And so, with the quantum analog, you would hope that you could find something a little bit more comprehensive and in that way gain an advantage, not just in the efficiency of its runtime, but in, its comprehensivity. Okay. We got a few more minutes left. I can quickly go over Monte Carlo stuff. Essentially, the Monte Carlo stuff is, if you want to do a bunch of simulations to say sample a bunch of data, you can run Monte Carlo simulations to just kind of randomly pick out your data to get a representation of the distribution data that you want to look at. The quantum analog of that, you can do a lot of these processes simultaneously. So instead of heuristically going through and sampling and getting these smaller distributions and cross-comparing, you can get representation closer to the overall distribution in less shots. And we're doing a lot of that work and finding, I think there's a graphic here where we do some comparison. Again, this is rescaled classical, right? So this is not, like the most robust classical comparison, but we are looking at this scale, at the NIST devices, we see we can get like lower root mean square errors on trying to make some prediction or trying to map out some distribution. Using
it's a huge thing. So I'm posting something in the link right now. And as far as financial too, could you touch on any of the other financial things?
Yeah, so that's an application area that we've looked heavily at, and there's a lot of interest in that. And one application area is in portfolio optimization. So if you wanted to, say, analyze the trends of whatever your investments are, basically, you kind of have to look at things individually, and then you can do traditional statistical techniques to do like averaging or some other measure to make sense of, to find an optimal for whatever the combination is for your portfolio, right? The quantum system, you can do it simultaneously. And you can also detect anomalies with the quantum method more readily that might be more informative, where statistically, like classical statistical methods might kind of have to smooth over and overlook.
Okay. Any questions from somebody that we haven't heard from? I saw Ravi, Jamie. Did Monte Gardner, did you have a question? And then it's just first come, first serve. We've got about 5 minutes.
I had a question while others are hesitating.
Go ahead, Phil.
Dan, so it's a question about Continuum Strategies. So you mentioned that you are hardware agnostic. As I understand it, the software you're developing is hardware agnostic, whereas on the hardware front, you're invested in trapped ion, the trapped ion approach. And you, in fact, on the website, position yourself as a full stack provider. So in the industry now, there's a certain amount of anxiety about full stack lock-in versus diversification for potential clients, especially for those companies that want to see themselves as being at the cutting edge of quantum adoption and so on. So do you have any advice for these companies? And could you clarify how Quantinuum sees itself in this regard?
Sure. Yeah, absolutely. So yes, it's true that we try to build our model as full stack software as a service solution because we have the hardware and we can scaffold, using that hardware. But we don't restrict ourselves to that. A lot of the research that we do, we don't run everything on our H-series hardware. We run on IBM hardware. We run on these other resources just as anyone else would using something like Ticket. We just can do that. It's sort of, it's something that we're building up, and we want to provide that full stack for those who are looking for that full stack. And, but at the same time, like we understand the fear of this vendor lock-in, and we want to cater to anyone regardless of the approach that they want to take. So all of our solutions are generally software based, and it doesn't really matter what hardware we're running on. Just at the moment, the best use that you're going to get out of the software solutions is running on H-series hardware, just because it can do the most. But that may change, and that's why we stay very agnostic, and we want to be, boosting anyone from any avenue, and we try to convey that to our customers as well.
Awesome. So Yeah, I do have another announcement, is this is the biggest audience we've had, thanks to Dan. So let's everybody thank Dan. And we'll have a last questions from Dan, and then same thing with everybody else.
All right, I'm going to flip forward then real quick and leave on this last slide because I am the partner manager. I told myself I would do this. We are building this partner ecosystem and channel partnerships. Please reach out to me anytime if you're interested in collaborating in R&D. You have a business that you feel like you could incorporate something like our cryptographic keys, or you want to make use of some of the molecular modeling that we do. Anything you have, please come to me. I provided my contact information. I can share this deck with everyone that's on this call, and you'll have access to the video. I'm sure Kevin will share as well.